last lecture, I gave a construction of Wigner function for one qubit, where all the operations are essentially constructed out of polymatrices, and there is a geometrical picture of the Bloch sphere for the whole set of states, and I showed that the Wigner function will be positive if you stay within the octahedron which is inside that Bloch sphere. The importance for that result is that the theorem which I mentioned, that if when Wigner functions remains positive during evolution, it can be efficiently simulated using classical reversible logic. This is the theorem. And so the question comes is, what are the things you can hope to get as an advantage when you go to a quantum system? Well, Wigner function has to become negative at some location or the other. And since we saw that the Wigner function for a qubit is positive inside the octahedron, the transformations which take the octahedron to itself will never be able to take the point which is inside the octahedron to somewhere outside. And that allows you to put some restrictions or what are the kind of transformations which will be required for quantum logic, which will produce an advantage. So let me now just construct all the transformations which can be efficiently simulated by the classical logic. So they are basically the symmetries of the octahedron. So there are the axes, x, y, and z. There is a sphere as well as I can draw, and then there is a octahedron which can be constructed by joining all the edges which connect the vertices on the coordinate axis, and there is a symmetric structure. The top state is 0, the bottom state is 1, and one can draw a picture. It's basically connecting all the edges. There's one here as well. And generically, the transformations convert some density matrix to U rho U dagger. For any density matrix, this is a representation of the density matrix, and we ask what are the symmetries of octahedron? Cannot take internal points outside. Rather straightforward fact. So now let us just list all the symmetries which can be visualized in various ways. So yeah, let me just list them. The easiest one to figure out is the rotation about the one of the coordinate axis by multiples of 90 degrees. Okay, there are 4 states inside that, so I will break it up. Rotation about coordinate axis by angle pi. So if I rotate about this vertical axis by pi, what it does is takes this x-axis to minus x-axis and y-axis to minus y-axis, and nothing happens to z. What is the transformation which will do that? So it's quite easy to see that sigma I, sigma j, sigma I is equal to minus sigma j for j not equal to I, and the transformation falls in this class because polymetrics are unitary. So you can identify that the transformation which rotates by this pi angle is nothing but transformation using a polymetric. So any logic gate which implements a polymetrics 1-qubit rotation will be a symmetry. Okay.
This is only for z-axis rotation.
Huh?
Is this only for z-axis rotation?
Any of the 3. You can put whatever label you want, I and j. 90-degree rotation about the axis is going to change the sign of the other 2.
J represents the axis about which we are rotating. J is the axis about which we are rotating.
Yeah, so there are 3 transformations here. If you say polymetrics sigma x, sigma y, and sigma j, if you lose that as a logic operation, they are not going to change the structure of the octahedron. So we are using this 1-qubit operation. There are what? 1 rotations of generic unitary type. But this says that if it is that unitary rotation is nothing but a polymetrics, it is something which is not going to give you quantum advantage. Then knowing this, one can now construct rotation by pi by 2, or actually there are 2 choices, whether it is plus pi by 2 or minus pi by 2. For pi, it doesn't matter, we go one way or the other, it's the same thing, but here the 2 operations are distinct, and as a matter of fact, they are inverses of each other. Nothing complicated in that. But we already saw that the rotation by pi is generated by the polymetrics and if you want the rotation which is half that, then the operator are nothing but square root of the Pauli matrix. It's defined. You can calculate the square root, and well, you need two, and they are just the inverses of each other. Both of them are unitary transformation. So if your logic gate is square root of a Pauli matrix, that is also something which can be generated efficiently by classical reversible logic. Remember that we use this kind of a square root transformation to reduce the Toffoli gate to 2-qubit gate. It is not available in classical logic, this transformation, but even if you include it in quantum logic, the transformation remains efficient in the sense that it will give you limited advantage but not arbitrarily large. That is the point. So this is actually, well, I will write that little later. What other kind of symmetry you can imagine? These rotations are now taken care of, but you can say that I can do rotations about something other than the coordinate axis, and that will also remain a symmetry. One of the possibilities is to generate rotation about the midpoint of an edge by connecting this edge to its diametrically opposite edge, kind of a bisector, and then ask what is the rotation about this axis with 180 degree going to do. It is a symmetry of the system. Okay. So this is a rotation about midpoint of opposite edges by angle which is pi. So now let us imagine what the effect will be. If I rotate about this axis be pi, these two points are going to get interchanged, and this one is going to land up on the negative side. Okay. You have to visualize the three-dimensional geometry. But it's an axis, you rotate it out by 180 degrees. This point ends up here, this point ends up here, and this point ends up on the other side. So it means interchange two of these labels and make the third one negative. Okay, so what it does is interchange two axis labels and flips the third one. Do we know any one qubit operation which does such a job?
X and Z. X and Z.
Yeah, you can take to be x and z. The answer is the Hadamard operation. It's a unitary operation. What this does, if the conjugate of Hadamard operator is itself, so H sigma y H is equal to minus sigma y. Okay, is going to anti-commute, and H square is 1. But if I do H sigma x H, I get sigma z, H sigma z, H is sigma x. So the Hadamard operator is also a symmetry of the octahedron. It's not there in the classical logic, but it's doing something which is limited even in quantum logic. What more you can imagine? Well, I took care of the edges about the symmetry, but you can also look at the center of this triangle faces, and then if I take any triangle and rotate by 120 degrees, I come back to the same structure. Okay, so and what will it do? Well, it changes the three vertices in a cyclic manner. X goes to y, y goes to z, z goes to x. So this is just a cyclic and this can go in again, both plus 2 pi by 3 or minus 2 by 3. So it is just going to do permutation. Okay. And this is nothing complicated, it's just relabeling of the axis. What you call x or y or z, well, you can choose your convention, it's not going to do anything. So this is actually not a logic operation, it is just relabeling, and which you can do and it will not change anything more. And well, you can ask, you took care of all the rotations, are there any other symmetries? And there are other discrete symmetries, all of them are related to reflections. Reflections which is not part of the rotation, and you can take care of all the reflections in 3 dimensions. So by using a so-called inversion operation, which takes r going to minus r. as a 3 vector. It can produce all reflections together with rotations. And what is that symmetry? And it is something which I mentioned. It is the what is called a conjugation. Sigma I goes to minus sigma I star. Remember, we are dealing with real labels. This is a symmetry of the SU2 algebra, but if you take all the coordinates to be real, this star is not going to do anything, and it just changes the sign of all the 3 coordinates. And so this is a complete list of all the symmetries of the octahedron. They are all taken care of in terms of this sort of elementary transformations. And what the theorem tells you that all these transformations can be generated efficiently using classical reversible logic. And that means that these are not part of classical reversible logic. But only give limited quantum advantage. And they are basically the square roots of the Pauli matrices and the Hadamard transform. And we used it used to reduce this C square naught to 2-qubit gates. So we have done that. So yes, it does simplification. This is a 3-qubit gate and 2-qubit gate. You can do simplification, and that gives you some advantage, but that is of a limited type. What does this stuff do? The Hadamard operator. And one of the common places where we have used this transformation is to generate Bell states. You construct a superposition 0 plus 0 going to 0 plus 1, and then you do a control knot, which is there in the classical logic. So this was a little circuit. H So yes, the Hadamard operator is useful. It can produce Bell states. Bell states are entangled states, but still that is only giving you limited advantage. It is an important lesson that entanglement is not everything in the story. You can create entanglement, but entanglement can be simple enough. As far as algorithm structure is concerned. And so, what do the quantum transformations require? And yeah, so these gates, all these symmetries generate what I labeled earlier as a Clifford group or one-qubit. And I had mentioned it quite earlier while talking about quantum gates, that the quantum gates which belong in this Clifford group are efficiently simulated, and they are not going to give a large amount of quantum advantage. So, we want a large quantum advantage. It needs something beyond this, and the choice which is used in many discussions as well as textbooks is a fourth root. Remember, you can make rotations about smaller and smaller angles by just keep on taking square roots. So pi was just giving polymetrics, pi by 2 gives you square roots, you make it pi by 4, which will generate something like this. It will just generate a smaller angle, and you can go down the hierarchy to as much precision as you want. But what can be shown, and I had pointed it out earlier, that if you go down to fourth root, that is enough. That is now capable to generate full algebra and not just the symmetry of the octahedron. And so this is a useful conclusion of this analysis, that yes, you can have various quantum gates, but how many of these gates you should choose as a sort of fundamental or basic gates which will now produce everything else which you need in a quantum algorithm. Well, going up to Clifford group is not enough. You have to go beyond, and taking one more square root actually does the job. And this it becomes a label for the computational advantage, or in other relations, computational complexity is how many of such gates do you need to use in an algorithm. If you don't use it, the algorithm is going to give you only a limited advantage. This is something becomes necessary to get advantage which will change the complexity classification. It doesn't mean that the advantages which you got over here are useless. They are going to give you something in practice. Only thing is, whatever it produces is limited. And we can actually, so this limited advantages can be in the so-called polynomial speed up in computational but it is going to be polynomial by this explicit construction. You are looking for changing the complexity classification. Polynomial things are not going to go much further. Okay. So this is as much as I can say about the properties of the Wigner function, and it goes back to all the things which we started with, why you want to construct quantum logic and what are the transformations you will use in the algorithms and all things of that sort. And it gives a justification for what we did in, well, just using algebraic analysis and various identities and things like that. You need to go beyond. Yeah. So now I want to say something about much more general framework of computation, which I described at the very beginning of the course, that concerns the subject of error correction. So there is actually going to be a whole course next term on error correction, so I'm not going to give you the full story, but the ideas which we have used in this particular introductory framework, they keep on repeating. Okay, and that is the part I want to emphasize, that how the same arguments allows you to perform error correction in the quantum logic. You are going to put together things in a particular manner, but yes, there are restrictions and you need to find ways to go around them in some sense or the other. So let me start at the very beginning, that why we need error correction. This is not just for the quantum computation, it's equally true for the classical one as well. And the reason for this is very simple, that no physical system is perfectly isolated and in thermodynamic sense, the perfectly isolated system will correspond to zero temperature. That you cannot reach. What does it has to necessarily involve? One of them is the controlling part itself, which for example gives the instructions. How are you going to address the system? Well, something has to be sent there. It is not fully isolated. So whatever these controls are there, there will be some measurement apparatus which tells you the property of the system. Of course, it has to interact. Otherwise, how are you going to get a measurement out of it? And on top of that, the rest of the universe, which is always present in addition to these explicit connections which you make in a specific design. And all this produce different kind of effects. They are disturbances. And the business of error correction is to control these disturbances so that the physical properties of the system get disturbed but the encoded signal can be protected. And as I said, these features are equally well in our classical devices and computers. You have to devise various strategies that yes, there are going to be some fluctuations and signal has to be protected. How do you do this? As a very simple thing which I had mentioned before. So the strategy is discretize the logical states and use bounded error computation. What you are doing essentially is the disturbances are there, but you are putting a bound on it. The disturbance is not zero, but it is within certain limits. What does discretization do is you make the states sufficiently far apart so that the separation is bigger than twice this error. So then the error, whatever it may be, is not able to jump from one logical state to another. And you have a protection. Both these things are necessary. You need discretization of the state. If the states are arbitrarily close to each other, then there is no way to protect their, because the fluctuations will take you from one to another.
So, but we will be preparing these states before the error comes.
Yeah.
So we have to have some
You have to prepare the error state also to this particular accuracy.
So we need to have some knowledge about what the error will be.
Yeah, you have to have a knowledge about what is the magnitude of the error, and in generic system, what is the direction of the error. Because some errors come in a certain set of transformations and not in some other transformation. So you need the knowledge of both. Okay. The initial state is also part of the game. That has to be prepared carefully as well. So all these things, initial state, evolution, and the measurement. They all need bounded error. Without that, this strategy doesn't succeed. So what are you implicitly assuming inside there? The implicit assumption is that you can separate the scale of the logical variables and the physical variables. The physical variables are going to remain within the bounded error. The logical variables are big jumps going from one state to another, which will do the encoding. And it is this separation of the two scales which allows you to implement this particular strategy. So, scales of error and encoded transformations are separated. And this is the fundamental part you have to include in the design. Okay. And as I said, whatever silicon devices have all these features inside it. If you ask what are the physical variables, there are some voltages and currents which are flowing around the electric circuits. They are all fluctuating, but what you call 0 and 1 are sufficiently far apart signal, like off and on. That off and on is not going to change just because the voltage fluctuates a little bit. There's a big jump in the voltage required to convert the off state to on state and vice versa. And that separation of what is the distance between 0 and 1 and what is the size of the fluctuation is absolutely necessary to produce this particular strategy. And this is the generic stuff, and we have to find its counterpart in quantum logic. Okay? All these ideas are the same. But how are you going to implement in the quantum logic? That is something which we can now talk about based on all the things which have gone through using various kind of quantum transformations. One thing I can point out that there is a separate subject or different strategy even in the classical case where you separate the two scales. That part is the same, but in a scenario where error is large and physical transformations are small, it just turns the whole thing on its head. And that also works. The point is that two have to be separated in some particular sense. And the quantum description of that kind of strategy is something called a decoherence-free subspace. There will be a global transformations which will have all kind of errors, but the variables are defined at a much smaller scale in this so-called decoherence-free subspace, and nothing happens to them. So that is something which I will leave out from this particular discussion. It can be illustrated separately in a different manner. Okay. So now I ask the question, how can I implement this in a quantum logic? We have to visit, can I do all these things? Some interaction, some transformation, keeping the errors bounded while implementing all these quantum gates. So, we need to, well, this is again more general, but I can give an overall scale. First, figure out what are the types of errors. Okay, so the types of interaction, decide the types of errors. And we have seen two generic kind of scenarios where the behavior of the error is controllable by essentially classical means. So they are roughly associated with two aspects of the quantum dynamics. So one aspect is this superposition, which is a property of waves. And we know that if you only have the wave dynamics, I can construct a classical version of it and do all kind of experiments as we did it in school, some interference and some what you call phenomena of amplitude manipulation like beats and things like that. No problem, you can observe it for a long time. So this has a high stability. on its own. The other feature which was constructed was tensor product of multiple components, and this is the particle aspect which is also there in the Boolean logic, discrete variables manipulated independently, and this is also highly stable on its own in the classical world. What we are doing in quantum thing is putting these things together and demanding that we have both of them at the same time. That makes the system highly unstable. So and so now you have to ask, can I handle these parts as well as I can before I try to mix them up? As soon as you mix them up, the whole thing is going to get out of control. The quantum lifetimes are extremely short. And now I can be more specific. There are labels which define what happens, and they are all connected with various types of error. What happens when the quantum system becomes unstable? So there are things, and we have seen many times that the quantum system can be described by the density matrix. And so experimentally, you can say that the density matrix elements basically decay or change their values. What does the experiment tell you? Okay. So now you look at various components, and what you find is the diagonal elements of the density matrix. They describe transitions between various states. Ground state, excited state, second excited state, they are all populations of the diagonal elements, and they change. So one of the common things you can say is that excited state is going to decay to the ground state while the diagonal element is going to change. So this produce, or well, not produce, but they change by transitions. And then you can ask how fast the excited state is going to decay to the ground state. These are numbers you can measure directly experimentally. So there is a time associated with that, which is typically labeled by the notation, and the dominant process for there is a excited state decay. And you can measure this experimentally, so you can say how fast the quantum system is going to get disturbed. And then there are off-diagonal elements. And many times there is a different name for the off-diagonal elements of the density matrix. They are called coherences. They also get disturbed. And the property of the off-diagonal elements of the density matrix is they can be complex numbers. The diagonal numbers are all populations. They are positive definite values, and all they can do is change from one population to another, described by decays. But these are complex numbers, and so they have phases. And you can observe what happens to these off-diagonal elements again by just experiments in handling quantum systems. And these are again observed to change on a time scale which is called T2. Okay. And the label most often used for that is decoherence. There are phases sitting inside here, and the phases, when they disturb, they become sort of distributions, some random fluctuations, and then if you observe them as a kind of average over the fluctuation, they all vanish, or rather decay at a certain rate. What is the time scales for that? It is called T2. And both of these are experimental numbers. In practice, you need to control both of them. Okay. And control in the sense that bounded. Don't want them to go arbitrarily outside, and from all the tricks that have been tried, it has been seen that controlling T2 is much more difficult than controlling T1. So this is kind of a generic label, but this terminology is there all over the place, and you have to understand why we are asking such questions. So now what do you do? Well, you have to protect again all the various things which I wrote down here. At least this controls and measurement are in your hand, so you know what you are trying to do. But this rest of the universe is not in your hand. You don't even know what the kind of interaction there may be. Okay. So the interactions are characterized or can be characterized by that we know that in any physical system, the interactions will have their steady states, which we call the eigenstates. If you are an eigenstate of the system, then you will remain in that particular state. And that basis formed by the steady state is given a name. It is called a preferred basis. The concept is that if you have a state in the preferred basis, the interaction will not do anything to it. And then you can ask in various scenarios, what is the corresponding preferred basis? And I go out of that basis, yes, there is all kind of things will happen, but if I stay within it, I'm reasonably safe. And well, we use most of the time to discuss all the states. The basis, which is the label, is energy. All the states you have discussed about various systems, you say that they are eigenstates of the Hamiltonian. Okay, then everything else is a superposition. What does the eigenstate of the Hamiltonian tell you? It is a state of fixed energy. Is there an interaction corresponding to it? That is there a physical property for which the eigenstates are states of different energy? And that is indeed the case. And the eigenstates of energy basically tells you which of the fundamental forces coupled to energy, and that fundamental interaction happens to be gravity. It's the gravity in the most general sense, which because the framework of general relativity in the most powerful sense describes the interaction as something which couples to the stress energy tensor. And one component of the stress energy tensor is what appears when you try to reduce it to the non-relativistic language. It is just the energy. So why we talk about energy? There is a particular physical interaction which drives you towards that scenario whether you like it or not. You can't turn off the gravity. And that's why you say that why I talk about excited state, ground state, etc. Why does it have to go to the lowest energy state? Well, there is a fundamental force which wants you to go in that particular direction. Can't avoid it. But you can ask any other preferred basis you can construct. Well, there are different interactions, and whatever they may be there will be a corresponding preferred basis, and you have to design various things. So gravity is an exception in the sense that it is always there, it is always attractive, which means it will take you the lowest states whether you want it or not. You cannot excite the state using gravity. But the other interactions are more powerful. You can go both ways, attraction, repulsion, all those kind of things are there. And other interactions, so all kind of things, non-gravitational interactions, they can be shielded. That's an important part, that yes, you want to cut down unwanted interaction, give a very nice shielding. Now, it goes in different ways. Well, it can be just electromagnetic shielding, which allows that electric and magnetic field cannot go inside, or it can even be a much more general scenario like a finite temperature bath. How do you shield against it? Go to low temperatures, because that interaction is essentially kinetic. It's an exchange of whatever energy and momentum with the environment or the bath, and you want to reduce it, well, you go down to low temperature. Yeah.
You mean to say some of the decoherences are dictated by gravity indirectly?
Yeah.
Should we perform any quantum computation in space? Can we evade the
It's not a what you call leading effect, in the sense that the force of gravity is generally much weaker than that of the other interactions. So yes, you don't have to really worry about going into space and cutting down that interaction. The point is that it gives you an idea about how the organization of states is in terms of energy. Why do you see it like that? And gravity does play a role in selection of that particular basis. The eigenstates of energy, for some reason or the other, are fairly stable. Okay, that's what you argue for. What you need is much more complicated, because you need all kind of transitions also. If you don't have transitions, then there will be no processing, no evolution, nothing of that particular sort. So that is where all these non-gravitational interactions will come in. So this is what you call electromagnetic shielding, low temperature, and yet another effect which is used is a large inertia of what are known as coherent states. So all of these things are used in many different scenarios, but this is the one which I can give examples of there are macroscopic states, quantum states, which are fairly stable, and two of the ones which are heavily used in technology is one of them is a laser, which is a coherent state of lots of photons all in the same state. And what that collection provides is a large inertia because everything is together in the same state. Another example of this kind of large inertia coherent state are superconductors, where there are lots of Cooper pairs, all kind of condensing into the same state, and if you shield them reasonably well by putting at a low temperature, they will remain superconductor for a long time. And this is also heavily used in technology, where you have these sophisticated machines, and where once you put them in a superconducting state, they can sustain the currents for years and years together. You don't have to do anything else. And the well-known examples are these magnetic resonance machines, where you once put them at low temperature and start the current. The labs here will show you machines which are working after that initial setup for 20 years. Nothing happens to them. All you need to do is shielding. And why? Because this large inertia of coherent state does not allow you to disturb them in any particular way. You cannot perform any disturbances which will cause transitions. That is a scenario. But these strategies are all used. So here there are lasers, superconductors, which are all used, but the concepts and ideas you just have to understand most of the time. And the kind of computer chips which people are trying to design, they use some of these ideas in some particular way, but there is a limit. And the limit comes from the fact that all these things are designed to protect against the rest of the universe. What are you going to do about control and measurement? That you can't avoid. It is in your hand what you want to do, but you have to design. Okay. And that now comes the question, what do you do to make them stable? And I will kind of list the features which are there in a quantum direction which you have to conquer. Okay. So one feature is the quantum variables, as we are treating them in the Hilbert space, they are continuous. We need to make them discrete, otherwise things are not going to work. And where is the discretization available? Well, not in the dynamics. The Hamiltonian is going to evolve in time with some parameters or all continuous variables, nothing is going to happen. The process which is discrete is measurement. Measurement projects against one of the eigenstates, and the eigenstates are very distinct labels. So you have to use measurement to be able to discretize the evolution and then control the errors. So and how does it work? Well, there are things you can look upon as a sort of consequences of measurement. If the state has gotten disturbed, initially it was in some eigenstate which was stable, then when you perform measurement, sometimes you will get the eigenstate with some probability, sometimes you will get some orthogonal state with some other probability. What does the bounded error concept means? That the disturbance is in some sense small, so the probability of the orthogonal eigenstate will be small. Most of the time it is in the eigenstate. So what it does, the projection gives two possibilities. One is a desired eigenstate, and then this is a unwanted orthogonal state. But you perform a projective choice to give this combination, and then these things are distinguishable. They are quite a separate scenario, and then you have to design an algorithm that here do nothing and here apply discrete operation to go back. Okay, if you know what the eigenstates are going to be, you will know what discrete operation will take you back. Okay. So this is the manner in which continuous variables are tackled. You have to put this some structure in the actual protocol. Okay, the protocol I am not giving right now. I am just describing that all these features have to be understand. The second thing is one of them is this continuous variables. You have to figure it out. The measurements are irreversible. So you will describe the unitarity of the process if you perform a measurement, and in the scenario you will lose something when you do that. And the point is that what can you afford to lose? I cannot afford to lose the signal, but I can afford to lose the noise. Okay, so this is happens to be a strategy where you must separate the noise and the signal. Okay, part of it is based on the first concept itself, but what you do is something which illustrated in the reversible logic scenario. So there is a state, and then you add ancilla. And here you rearrange. So this is some measurement machine. And what it does is, this is a rearranges this stuff, that the state is purified, the ancilla becomes noisy. And then what you do is wipe this thing out and keep this purified state itself. It's very similar to what is done in filtering. You have some state. You add some extra variables, transfer all the things which you don't want to it, and then throw that thing out. And filtering is quite common, I mean, whether it is in the kitchen where you try to remove the what you call dirt from your grains, or it can have a sophisticated analog in electromagnetic signals. Well, there is a noise, but you know how to separate it. You separate it and then you have to throw it out. That is the irreversible part, is throwing it out. And the remaining set, of course, it is smaller than initially what you put in, but that remains protected. So this is filter. But you have to do that.
And always a chance that the noisy ancilla bits and the pure state are entangled.
They are entangled. They are entangled until you throw it out.
Even if you throw it out, they are entangled.
No, you erase it. That is the irreversible part. You are destroying part of the system. This is a measurement. And in perform a measurement, the entanglement is destroyed. It's not there anymore.
So there isn't any requirement of the reversible inverse.
No, there is no. You can design M inverse, but what you do is discard. That is the important point. If you don't discard it, it will come back.
No, but in that case, some signal will also be destroyed, some portion of the state will also be destroyed.
Yeah, so that is how to design this filter properly. Okay, many times what you are interested in is that the filter may not be perfect. But what is enough is the noise goes down. Okay. That can then be pushed further, that yes, you reduce the noise level and then you can have more practical use for whatever remains.
Design such that the entanglement between the pure state and the noisy ancilla is this.
And this is still going to be designed in a unitary fashion. So nothing is discarded over here. Only after you go to this final state, which is entangled, then you throw away the ancilla, and that is at the place where irreversibility comes in. Filter, whatever we are going to use, are all still going to be unitary processes.
So the objective should be, the filter should do such work that the entanglement between pure state and the noisy ancilla is less.
Yeah, not less. It can be whatever it may be. but the noise has been transferred here. But the signal is remaining over there. Remember here, the state had both noise and the signal in it. Somehow you managed to transfer the noise without transferring the signal. And how that is possible, it goes back to this continuous variable discretization. First, I know where the noise is because I can label these eigenstates in somewhere. So here, the unwanted part is the noise, and somehow I'm transferring it over here. These are all correlated steps, but you have to pay attention to it. And further restrictions is coming from the that the number of errors in the quantum Hilbert space is much larger than that in the classical reversible logic space. That is just because the number of directions which you look at are many more. So classically only bit flip. For a single bit, all you can have as an error is 0 goes to 1 or 1 goes to 0. Nothing more you can do. Here, qubit has 3 poly channels. In contrast to here, bit flip can be understood as a, say, matrix sigma 1. There's a change is 0 and 1, but now you have 3 in case of a poly scenario, sigma 1, sigma 2, and sigma 3. You have to tackle all of them. There is not much else. So the errors are more. Well, you figure out how to handle multiple errors as well, and that is fine. It can be done. And one more thing which you need to tackle is this constraint of no cloning. So one of the simplest strategy in our classical world is, well, if the first time you don't succeed, you repeat the process. Goes in many different ways. In communication, I tell you something, you don't understand, you ask me again, I repeat. Maybe different words slightly, and ultimately that thing succeeds. But in quantum case, you have this no cloning theorem, which says I cannot make exact copies. So the just simple-minded repetition is not going to be the solution to the problem. So, well, this is the sort of challenge, and there is a solution. So this problem or solution was constructed by Peter Shor again, a few years after he discovered the factorization algorithm. And according to him, this was a much more important construction than his factorization algorithm, because it allows you to explicitly say that I can do non-trivial things on a quantum device in presence of errors. And it's a very straightforward scheme. He was the first one to put it explicitly, and then of course many people then build on these ideas to define all different types of error correction protocols. But the outcome of this thing is it allows construction or other formulation of what is known as a fault-tolerant computing in presence of bounded errors in initialization, all the things which I evolution and measurement. All the three things you have to tackle, and then the important question is, when this is a subject which is now, well, something where books are written, so defining all kind of scenarios and working out the bound for every protocol which you design, how much error you can tolerate. That is a crucial question. So, crucial property is tolerant and how is it defined? That if the error is less than this particular bound, then my whole computation will remain protected and it can run indefinitely even on an imperfect physical device. Device will have noise, but my computer won't crash. Of course, you are not asking for an indefinite thing. If computer runs long enough, fine, it can crash, say, once in a few days. We don't mind it, for our PCs, etc. But it should not be that it crashes for some microsecond or some time scale. So that is where the value of the error bound is important, and there is a theorem that can prove, which says that if the error is less than this particular bound, then your computation will remain protected indefinitely. In real world, you are not looking for indefinitely, but fine, theoretically you can prove. And then the question is, what is the value? How much you can tolerate?
By crashing, you mean getting jumped in the output of the computation, or computer itself stops?
Computer stops, in the sense that the result which you get has no meaning whatsoever for the output that you are looking for. It just gives you garbage, whatever it is. And different protocols are now designed, or people still keep on designing to make this tolerance limit as large as possible. So for the so-called circuit models, which are used with all the logic gates of the type which we have seen, this number is estimated to be about 10 raised to minus 4. Okay. And then there are proposed designs using topological system where this number may be larger, 10 raised to minus 2. What do this number mean? That these are the precision values for individual components of whatever device you make. So this and the challenge now is in the hardware part. Can you make that one particular logic gate which has an error, say, less than 10 raised to minus 4? That is where everybody is stuck. Millions of dollars have been invested to get this physical system to have such small errors. Nobody has reached that level. Okay. So whatever announcements you see from various companies, IBM, Google, whatever else, some photonic computers from Xanadu, etc., they are still not able to reach these particular values. So no demonstration has actually included error correction. All the results that are put forward are implemented on noisy systems without any error correction. That is a sort of current status. Of course, people keep on saying that we are working hard, we are improving our design, and we will ultimately get there. But yes, it is a problem for the future. And that is roughly the status of the field. But I wanted to give an overall picture of how things are and what is that we want to address. And this is a background in which the whole subject of error correction is formulated. And yeah, there's one more lecture on Wednesday. Maybe I will describe the simple example which constructed by Shore. It is not too complicated, but it brings in all these ideas, how it is done. So, it's a small system. You ask for just 1 qubit and what you can do with that, but it illustrates all the ideas and see how things can be designed. But these bounds are not there for even for the small system in something which can be reached. So even this 1 qubit, nobody has designed sufficiently clever hardware which can protect 1 qubit. You forget about protecting large system. So I will give a, well, it should not be too complicated. It's something I can describe quickly, and I will give that example in the next class. But as I also said earlier, any questions about anything which went on in the course, just let me know, and I will address all of this also in the next class. That will be the last class of the course.
How this not only is happening using the Shore's formulation?
No, I didn't understand the question.
You said when you classically we can repeat
Yeah,
when some information is lost.
yeah,
Because of mechanically it's not possible because of no problem.
yeah. So you have to use a strategy which is not repetition.
So how
So-
it shows correlation of this.
Yeah, so showed how to do it. It uses entanglement. Entanglement gives something beyond repetition. And that extra correlation which is there allows you to protect the code. If you don't use it, then it doesn't work.
Suppose we have to multicast an information from one source to multiple sources.
Yeah, so there will be always overhead. Okay, so, but what you are doing in all these places is something which can be called add redundancy. Repetition is a type of redundancy. Okay, you paying some extra price because one attempt was not enough. You invested more, but now you add redundancy in a clever way. That yes, you have to add redundancy. Without that, it's not going to work. But you add the redundancy, which is different than repetition. So yes, you are going to add something to take this code through, but it's not just repetition. There is a redundancy which has to be added, but it is of such a type that it involves entanglement. It is not repetition, and the algorithm works.